The topic we want to do for this first video is working with prime numbers and prime factorization. When you work with prime numbers, a prime is a number that has factors of only 1 and itself. A composite number would have factors other than 1 and itself. 1 is neither a composite nor prime. It's like the exception to the rule. So what I want to do first is list some examples of prime numbers. And since 1 isn't prime or composite, we'll start with the number 2. The next prime would be 3, then 5, 7, 11, 13, 17, 19, 23, and so on. This gives you an idea of some of the first primes, the ones that you'll probably be looking at when we do some of the prime factorization. Anytime you have a composite number, you can start by factoring it into other factors besides 1 in itself. So one of the things we'll do is go ahead and factor 18 and 24 into what we call a product of primes. We'll start with another pair of factors. So for example, we might break 18 down into 6 times 3. And then you want to keep breaking down each composite number that's a factor until you only have primes left. 6 can be broken down again into 2 times 3. 3 is already prime. So all the numbers that we have at the end are considered prime numbers. You can go ahead and write that as a product of primes. 2 times 3 times 3. Often they'll want to do it using exponents, so you may see this written as 2 times 3 squared. What you'll notice is this kind of looks like a tree. So it's called a tree diagram. And at the end, what they would consider the leaves are where you're going to find those prime numbers. Let's do the same thing with 24. You can start with any pair of factors that you want to break this number down. I'll start with 4 times 6. I can break 4 down even farther. I have 2 times 2, which are both going to be prime numbers. And for 6, I have 2 times 3. All the values that we have at the end are going to be prime values. So we're done breaking it down. We have 2 times 2 times 2 times 3. Or you could write it as 2 cubed times 3. These represent the product of primes for our two numbers. Now what would happen if you didn't start out with these same factors? So let's say we're going to take a look at 18 again, but instead of using 6 times 3, we'll start out with a different pair of factors. Another pair of factors for 18 is 2 times 9. So let's say I started there. 2 is already prime, but I can factor 9 into 3 times 3. So what I have, 2, 3, and 3 are my final prime numbers. That's the same thing we had when we used the factors 6 times 3. So it really doesn't matter how you start, regardless of the factors you choose at the beginning. When you finish, the product of primes is going to be the same. So any factors to begin with will be fine. So here's what we had for our product of primes. What we want to do is talk about how you can find the least common multiple for these. And we'll show you why in a minute. For the least common multiple, I want to look at the primes that I have. This one we have 2 and 3 for 18. And 24 is also made up of the primes 2 and 3. So for my least common multiple between these two numbers, I'm trying to find a value that both 18 would go into and 24 would go into as factors. I'm going to need to use all the primes that I see, so 2 and 3 are in both, and then I want to use whichever one has the most. So when you're taking a look at this first one, here's 2, it's just to the first power. Here we have 2, and it's to the third power. We have more of these. There are 3 2's multiplied together. So I'm going to need to make sure I use whichever one has the most. We'll be using 2 cubed. Do the same thing for the 3's. Here we have 3 squared, and here we have 3 again to the first power. 3 squared is going to be more, so I'm going to use the 3 squared. I can go ahead and multiply these. I've got 2 cubed or 8, 3 squared or 9. So it looks like 72 is going to be your least common multiple. 72 is a multiple that 18 goes into and also 24 goes into. So it's going to be something that they have both as factors. The reason you might want to find that least common multiple is when you're using fractions. One of the things you're going to want to do anytime you are adding fractions is find a common denominator. And for these, a common denominator is the same thing as a least common multiple. Now we're using the number 24 and 18. Those are the numbers that we just did the prime factorization for. And we found their least common multiple as 72. So I can rewrite these by using that least common multiple. We said 24 was a factor of 72. So 24 times 3 is going to give me 72. And I'll also need to multiply 7 times 3. Whatever you do to the top, do to the bottom. So our equivalent fraction is 21 over 72. I want to multiply 18 by 4. Again, whatever you do to the denominator, do to the numerator. 18 times 4 will give me 72, that least common multiple. And 11 times 4 will give me 44. You can go ahead and combine these. I have a common fraction. (65 over 72). And that we've used that least common multiple from the product of primes in order to find the denominator for our fractions. Another thing you might want to use the product of primes for, instead of finding just common denominators, is typically with really large numbers. Something like 72, if you were working with 18 and 24, you might easily find by listing some of the multiples. You don't have to go too far until you find one they have in common. But when you're working with a really large number, like 2,520, finding out what it has as its primes might be important. So let's go ahead and take this one, and let's find the product of primes for this number. You might want to start by looking for something that you know is going to go in here. Since it ends in 0, you can use some of your divisibility rules for these. I know I'm going to be able to take a factor of 10. So I'll have 10 times 252. Now again, learning some of the divisibility rules will help you as you're trying to break down this number into factors. But you also have your calculator. You can try different things and see if it's divisible. 10 I know I can break down into 2 times 5. And 252 is going to be an even number. It ends in 2. So I can take 2 out of it to start with, and I have 126 left. Again, keep going. I can keep breaking things down. I have 2, 5, and 2. Those are all prime. But I can break down 126. It's still even, so I can take 2 into that. And I have 2 times 63. 63, now you've gotten to one of your multiplication facts. 63 is 7 times 9. 7's a prime number, but 9 we can break down to 3 times 3. You want to keep going with each of your numbers until you have only prime values left. Here's what we've got at the end. We have a lot of different primes this time to make up our product of primes. Notice you've got the value 2, 1, 2, 3 times. You have the value 3 twice. You also have a prime number 5 once and the number 7 once. So I can write this as a product of primes, 2 cubed times 3 squared times 5 times 7. Here's an example of a GRE question that would use this idea. Which numbers are greater than the sum of all the prime factors of 2,520? List all possible choices. Now notice for this, when it tells you to list all possible choices, all of the values that you have those square boxes around them. So you know you can pick more than one answer for this choice. The values we had were 2 cubed, 3 squared, 5, and 7. That was our product of primes. They're asking you about the sum. So for this, I'm going to need to add all those values together. I'm going to be adding 2, 2, 2, 3, 3, 5, and 7. My total is going to be 24. So the sum of all those prime numbers is 24, and the question asks me to pick numbers that are greater than the sum. Well, looking at my choices, I have 15, 18, 24, which is actually equal to your sum, and they want the ones that are greater than the sum, 27, so that would be a choice, and 32, that would be a choice. So for this example problem, we'd have two values. D and E are going to be the choices we'd select to be greater than the sum 24.